Welcome to Naradar Academy. In this video, we are going to discuss compact sets in the real line R. Okay, so in this video, I am going to discuss a few important theorems in compact sets, and then I am going to discuss few problems, that is how to identify a given set is compact in R or not. Okay, first let's start with the definition. Let S be a non-empty subset of R, then S is said to be compact if every open cover admits a finite subcover. Okay, that means, see, I am taking one non-empty set. This non-empty set is going to be covered by an open cover. Okay, open cover means union of open sets. Okay, right? So for whatever set you are given, you find out an open cover. That open cover may be finite or infinite. Okay, that is union of open sets. Suppose if from that open cover you can choose only finite open sets which again covers S, then that set is said to be compact. Okay, so obviously you can find the open cover for any given subset of R. Okay, so every subset will definitely has a open cover, but for being a compact set, the set has to be covered by finite open cover. Okay, only when you have a finite open cover, that set is said to be what? Compact. Right, this is the definition, but for doing problems it's very difficult to identify whether every set has a finite subcover or not. So first let's see some of the theorems, and then using the theorems we are going to say whether the given set is compact in R or not. Okay, first let's start with the first theorem. Every compact subset of R is closed. So compact set in R means what? It is closed. So let S be a non-empty compact subset of R. Okay, what I have to prove? This S is closed. So S is closed means, that is, we have to prove R minus S, the complement is open. So for proving a set to be open, what you have to do? You take an arbitrary point P in R minus S and you prove there exists a neighborhood P minus epsilon to P plus epsilon completely contained in R minus S. Okay, that is, for proving a set to be open, you have to prove the set contains neighborhood of each of its points. So for that I am arbitrarily taking one point P belong to R minus S. I am going to prove P minus epsilon to P plus epsilon is contained in R minus S for completing the proof. Okay, right. Now, what I am going to do is, this P is a fixed number in R minus S. Now, you choose an element of S. Okay, X belong to S. Then define epsilon X is equal to half modulus P minus X. See, this is my P. Okay, this is my P which is in R minus S, and this is my X in the set S. Okay, now how I am defining epsilon X? Epsilon X is nothing but half the distance between P minus X. That means this is the distance between P and X. No, you take half of the distance equal to epsilon X. Okay, then with this epsilon I can find a neighborhood for P and a neighborhood for X. No, so P minus epsilon X to P plus epsilon X, this is a neighborhood for P and I am taking it as Gx, and I am taking neighborhood X minus epsilon X to X plus epsilon X, and it is a neighborhood for X. So what I am doing here is, see, P is a point in R minus S. No, for that point I have to find a neighborhood P minus epsilon to P plus epsilon which completely lies in R minus S. Okay, so for that I am going to move little by little towards R minus S by defining neighborhoods like this. Okay, so here Gx is a neighborhood for P and Hx is a neighborhood for X. This is a point of R minus S. This is a point of what? S. These two neighborhoods are definitely disjoint, because by the definition of this epsilon X itself you can understand the neighborhoods will be like this only. Okay, so these two are disjoint neighborhoods of P and X. Okay, so for P belong to Gx and X belongs to Hx, G intersection H is what? Empty. Okay, right. And this Hx is there, no? For every X in capital S, you can define Hx like this. P is fixed, but this X is a point in S. So if you vary this X, you can get a family of open covers for S. Okay, hx form an open cover for S. But S is compact given no, therefore this open cover admits a finite subcover. So let us take the finite subcover as hx1, hx2, etc. union hxn. Okay, let this be equal to h. So this S is contained in this finite subcover h. Now let's come back to G. G is a neighborhood for P, no, Gx. So by varying x, you will be getting different Gx1, Gx2. That is, for this hx1, you will be having one Gx1. For hx2, you will be having Gx2, etc. For this Gxn, you will be for this hxn, you will be having Gxn. Find out the intersection of all these neighborhoods. All these are neighborhoods for P only, no. So intersection of neighborhoods of any point is again a neighborhood. So this intersection is also an open set containing P. Now I am arriving at two open sets. One is H, another one is G, whose intersection is empty. That is, they are disjoint, and P belongs to G. That is, G is a neighborhood for P. Okay, and G intersection S is also empty, no, because what? G is completely contained in R minus S. Therefore, P belongs to G contained in R minus S. That means I have obtained a neighborhood for P which is completely contained in R minus S. Therefore, P is an interior point of R minus S. But this P is an arbitrary point, no. Therefore, every point of R minus S is an interior point for itself. Therefore, R minus S is open, which implies S is closed. Therefore, what do we conclude? Every compact subset of R is closed. Okay, the proof is very simple. That is, we take one point in R minus S and we take all the points in S. Okay, we define neighborhood for P and X such a way that their neighborhoods are disjoint. Okay, that is how we arrive at the proof. Okay, then next theorem. Every compact subset of the real line is bounded. In the previous theorem, what we have proved? Every compact subset is closed, we have proved. Now we are going to prove it is bounded. So let S be a non-empty compact subset of R. So that means what? Every open cover admits a finite subcover. So let me take the intervals minus n to n be an open cover, be an arbitrary open cover for S. So this is an open cover, means since S is compact, this will also have a finite subcover, no. So I am going to take the finite subcover as minus n1 to n1, minus n2 to n2, etc. minus nk to nk. Because the open cover is like open intervals only, no. So if you are taking a subcover from this, it will also be in the same format only. So this is a subcover. Okay, this n1, n2 are what? Natural numbers. So you choose k equal to the maximum of n1, n2, n3, etc. up to k, nk. Then obviously your S is contained in the open interval minus k to k. That means all your x in capital S are lying between minus k and plus k. That implies S is bounded. So what we have proved, every compact subset of R is bounded. So we have proved, first theorem we have proved every compact subset of R is closed. Now we have proved every compact subset of R is bounded. Okay, next important theorem is Hein-Borel theorem. This is just like a converse of the previous two theorems. Okay, the closed and bounded interval AB is in R is compact. We have closed and bounded interval, no, this is compact in R. Okay, so for proving it is compact, what we have to prove? Every open cover for this admits a finite subcover. So let script G be an arbitrary open cover for the interval AB. We have to prove it admits a finite subcover. I am going to prove this in 3 different steps. So in the first step, what I am going to do is I am going to define a set S. Okay, how I am defining? See, this is an open interval starting from A and ending at B. No, I don't know whether it has a finite subcover or not. So what I am going to define is S be the collection of all X. Okay, such that this X is less than B and A to X, the interval A to X is covered by finitely many members of G. That is, this A to X admits a finite subcover. Okay, I am not sure whether this admits a finite subcover or not. So I am just collecting the elements of X for which the interval A to X is admits a finite subcover. Okay, obviously A is an element of S because A satisfies all the conditions for the set. So A is an element of S, therefore S is a non-empty subset of R, and for every element of X, it is always less than or equal to B only. Okay, therefore it is bounded above by B. But order completeness property we know, no? What does it say? If you have any bounded set of real numbers that has a supremum, So this capital S has a supremum and I am going to take it as small s. Okay, this is the step 1. So in step 1 what I have done, I have defined one set S such that the interval a to x is covered by finitely many members of G. Okay, and I have arrived at the decision that this capital X has a supremum small s. And in the step 2, I am going to prove this actually the supremum S is equal to B. Okay, suppose as a contradiction, if S is less than B, then see script G is an open cover for A, B, no. Therefore, for every element in this interval, there exists a open set. So, for this S also, since S is less than B, for this S also, there exists a open set G alpha in the open cover. Okay, that is S belong to G alpha, and G alpha is an open set, no. So by what do you mean by open set? If a set is open, for every point in the set there exists a neighborhood which completely contained in that set. Therefore G S minus epsilon to S plus epsilon is contained in G alpha. Now I am choosing this epsilon to be less than B minus S, that is S plus epsilon is less than B, that is S is here. Okay, this is my assumption, S is less than B. I am choosing epsilon such that S minus epsilon to S plus epsilon is contained in G alpha. Now S is a supremum for S, no. So that means what? It is a least upper bound. That means any number less than S cannot be an upper bound. Therefore S minus epsilon cannot be an upper bound for capital S. So cannot be an upper bound means what? There exists a number T in capital S which is greater than S minus epsilon. Okay, now you see T belong to S implies what? What is the condition for a number to be in S? Interval A to T is covered by finitely many members of G. Okay, so now you consider A to T, closed interval A to T. This is contained in Gi1 union Gi2 union Gim. This is I am writing by definition of the set a capital S I have defined in step 1. Okay, now see, so, my T is somewhere here. Okay, A to T is covered by finitely many members of G. So what about A to S plus epsilon? It is covered by A to T union with S minus epsilon to S plus epsilon. But A to T is covered by Gi1 union Gi2 etc. Gim union with, this is contained in G alpha, no. Okay, this is M number of sets plus one more set. That means M plus 1. M plus 1 means what? Only finite number, no. Therefore, it is this A to S plus epsilon is covered by finitely many open sets. But this is half open interval, no. That is A to S plus epsilon. Okay, so what I am going to do is, if this is covered by finitely many members, I can find a C, okay, in between S to S plus epsilon. This is S plus epsilon. I can find one C in between S to S plus epsilon such that this closed interval A to C is contained in A to S plus epsilon. Why I am choosing the C means I want to arrive at a closed interval. Okay, then only I can say it is an element of capital S. Okay, right? Therefore, this is contained in A to S plus epsilon. This is open interval, that is our ordinary brackets. Okay, right. Now, A to C is contained in this, no, but this is covered by finitely many members. Therefore, A to C is also covered by finitely many members of G. Therefore, by definition of capital S, C is a member of capital S. But C is greater than S only, no. That is how I have chosen. C is greater than S and it belongs to S. This is a contradiction because S is the supremum, no. Why this contradiction arrives? Because I have assumed S is strictly less than B. Therefore, it is not possible. S must be equal to B. So, I have proved the supremum of the set is equal to B. Now, it remains to prove that the interval, closed interval AB has a finite subcover. So, for that, let G beta be an open set in script G which has the number B. B belongs to GB. Now, there exists epsilon dash such that B minus, because this is an open set, no, so it contains a neighborhood for B. B minus epsilon dash to B plus epsilon dash is contained in B. Now, again the same thing I am going to repeat as in step 2. Since B is equal to S equal to the supremum of S, there exists a D such that D lies between B minus epsilon dash to B. Okay, therefore, this closed interval A to D is contained in Gj1, Gj2 union Gjn. It is covered by finitely many members because D is an element of S. Therefore, the closed interval A to D is covered by finitely many members of capital script G. Okay, then what about AB? AB is nothing but AD union with B minus epsilon dash to B plus epsilon dash. This is covered by N n elements, and this is covered by G beta. Therefore, the closed interval AB is covered by n plus 1 open sets. Therefore, it admits a finite subcover. Hence, it is compact. So, what we have proved? The closed interval AB is compact in R. Next theorem, this is generalization of Hein-Borel theorem. Every closed and bounded subset of R is compact. In the previous theorem, we have proved closed and bounded interval is compact. Now, this is any closed and bounded subset of R is compact. Okay, the proof is very simple. Let S be a non-empty closed bounded subset of R and script G be an open cover. Okay, now S is bounded implies what? It has an upper and lower bound. No, let minus k and plus k be the supremum and infimum and supremum. Then S is contained in minus k to k. Now this will become a closed bounded interval in R. So by previous Hein-Borel theorem, this is compact, right? Now S is closed implies what? R minus S is open. Now R minus S along with this G, union G will be an open cover for R, isn't it? The real numbers. Therefore, it will also cover this interval minus k to k. Okay, but this is compact by Hein-Borel theorem. Therefore, this open cover admits a finite subcover for minus k to k. If that is a finite subcover for minus k to k, S is a subset of this set, no? Therefore, it will be a finite subcover for S also. Therefore, S is compact. So that's all. So collectively what we have seen here is, this is the final thing. The closed and bounded subset of R is compact. Okay, right? Now let's see some problems. That is, we are going to check whether the following sets are compact in R or not. See, first one is closed interval 0 to 1. Yes, this is compact because this is closed and bounded interval, no. Next one is minus 1 to 1 union 2 to 3. This is also compact because yes, it is bounded and it is also closed because union of two closed sets is closed. Next, Z is not compact because it is closed but it is not bounded. Next one, this is half open interval, now open at 0, closed at 5. So this is not compact. Next, Q is also not compact because this is neither closed nor bounded. N is also not compact. This is closed but not bounded. Next, this is half open interval 2 to infinity. So this is neither closed nor bounded. Therefore, it is also not compact. R is also not compact because it is closed but not bounded. Next, 1 to etc. 100. This is a finite set. No, every finite set is closed and bounded. Therefore, it is compact. And the same thing here I have repeated. Every finite subset of R is compact because it is closed and bounded. Okay, that's all. Thank you.